Our next speaker is Surhud and he'll tell us about the Subaru Hyper Suprime-Cam Survey.
Yeah, so thanks a lot. Unfortunately, this movie doesn't work out that great here. So I'm going to talk today about the cosmological constraints from the Subaru Hyper Suprime-Cam Survey. Of course, I'm talking on behalf of the HSC survey collaboration, and a lot of work had to go in so that I can talk about these cosmological constraints, especially from the HSC software team, the photometric redshift team, as well as the HSC weak lensing team. So I'm standing here as a representative for them, but the first paper that came out on these cosmological constraints, this is the phone number. It was led by Chiaki Hikage. He did a lot of the effort in pushing this paper out. So please take a look if you're missing some of the details. So let me begin. Okay. So let me begin by talking about, or by laying the foundation. Of course, we know that Planck gives us some of the best constraints on the cosmological model, and it tells us about this particular pie chart that we live in a universe which is dominated by unknowns. So instead of a universe, it's somewhat of an unknown universe. And I would like to understand these components, especially dark matter and dark energy, how much matter is there in the universe, what are the amplitude of density fluctuations in the universe, as well as the behavior of dark energy itself. So in this talk, what we would like to understand is how we go from these fluctuations that we have seen at a very high redshift to structures like these. So this is the later universe, which was seen by the Hyper Suprime-Cam instrument on Subaru. We would like to understand how cosmic structure evolves into something like this. So to give a summary of a kind of a toy model to understand why we are doing these things, if we take Planck, okay, so the Planck cosmological model, and instead of assuming a flat lambda CDM universe, if we say that there is an evolving, there is a dark energy equation of state given by this parameter called W. So instead of a cosmological constant, there is a W there. Then you can ask, how do amplitude of fluctuations grow as a function of redshift? So models from Planck, if you vary the W parameter, they make precise predictions of what these amplitude of fluctuations would be. Okay? So if we have measurements of these fluctuations at intermediate redshift, so somewhere between 0 and redshift 1, then you can actually constrain the cosmological model. We can constrain something or learn something about dark energy. So that is basically the premise that we work in. And so we would like to measure these amplitude of density fluctuations. Now there are various ways to measure these amplitude of density fluctuations. The one that I'm going to focus on today is weak gravitational lensing. I know that you have heard lectures about this from Alan in the school. But let me give you a short summary again. So these are galaxies that you see here are in different colors, and you can have galaxies at different redshifts. So that's this particular direction. So the light rays which are coming from these galaxies, they get deflected because of the presence of these dark matter blobs in between. And that shape distortion is something that you can measure in the observed sky today. It turns out that gravitational lensing is most efficient for lenses which are midway in between. So what you can do is, if you know where these galaxies lie, then you can do a tomographic reconstruction of the dark matter distribution. So for example, when you look at galaxies here, their shears will tell you something about the dark matter here. If you look at galaxies which are a little bit further in, then you can know about the dark matter a little bit further in. So that's the way you can map out the amplitude of density fluctuations as a function of time in the universe. So that's what we aim to do. So to measure density fluctuations, you need a great survey. And so we are lucky to have the Subaru, we are lucky to have access to the Subaru Telescope. So this is a 8.2 meter telescope located at one of the best locations in the world to do this kind of astronomy. It's at Mauna Kea in Hawaii. It's about 4,200 meters above the sea level. Quite extreme conditions there if you want to observe from there. But this particular telescope, it got a prime focus instrument called a Hyper Suprime-Cam. So this has one of the biggest field of view on an 8-meter class telescope. So we have about a field of view of 9 times the size of the full moon, 1.78 square degrees. So that allows us to conduct these wide surveys, wide imaging surveys with this particular instrument. So we are conducting a deep survey. We are doing imaging in 5 bands, G, R, I, Z, and Y. And our limiting magnitude in the I band is about 26. Okay, so this is like a precursor to something that would be possible with the LSST in the near future. Okay. Since we are doing imaging, again, we want to measure these shape distortions, we need excellent observing conditions. And so what I'm showing you here is from the first data release of the Hyper Suprime-Cam survey. These are our 6 different fields, and over time we'll get them to be contiguous. What you're seeing is data from 140 square degrees, and the colors here represent the seeing distribution. So just to guide your eye, this is 0.4, this is 0.5, 0.6, and then here's where we get out to 0.9, right? So our competitor here is the dark energy survey experiment. Right, so their median seeings are at this particular range. So you see how well we are doing in terms of imaging quality with the Hyper Suprime-Cam instrument. There are times when the seeing was so good that we had to actually think about how to cleverly use these shapes because our pipeline was not good enough. So we needed to do quite a few improvements to make sure that the PSF measurements and so on, they are done properly. So our median seeing is about 0.6. Okay? So this is a great improvement. But what we are doing is 140 square degrees compared to DES, which is doing a shallower survey but much wider. Okay? So we are complementary in some sense as well. So in order to do the HSC cosmic shear analysis, we need to make Redshift bins. So these are 4 different Redshift bins that we do. So from 0.3 to 0.6, go from 0.6 to 0.9, 0.9 to 1.2, and 1.2 to 1.5. The median redshifts for each of these bins are written here. But because we go down to such a deep, such depth, we have a median redshift for all of our survey, which is about 0.81. In terms of the number density of galaxies, we have about 18 to 19 galaxies per square arc minute. This again should be compared to something like DES or KIDS, which have less than 10 galaxies per square arc minute. So that's the gain that we get by going deeper compared to these other surveys. So these bins that we do, they were done by using photometric redshifts. So we have measured these 5-band imaging information. So for each galaxy, we have G band flux, R band, I, Z, and Y band fluxes. So we take fluxes and then we turn them into photometric redshift estimates. So this is like a poor man's spec Z. And then we use those point estimates to then define these bins. But of course, you won't believe me if I say that these are exactly the same redshifts that these galaxies lie at. So we need to do something to infer the true underlying redshift distribution of these galaxies. So for that, what we had to do is we had to take a region of the sky where we have better photometric redshift measurements. So this was the Cosmos region. The Cosmos region has been imaged in multiple wavelengths. In fact, it has 30-band photometric redshift informations. So we take those galaxies, and we have observed these same galaxies with the Hyper Suprime-Cam instrument. So what we can do is we can remap the galaxies that we see in Cosmos to the galaxies in the HSC weak lensing sample. You can use the 30-band Cosmos photoz's as the ground truth, and then we can work out what is the true redshift distribution of our HSC weak lensing sample. So that's what you're seeing here. So the actual bins are shown with these shaded regions, but the inferred redshift distributions are shown by these histograms here. So you see that there is quite a bit of overlap between the different redshift bins. And so we need to model these quite accurately in order to get the cosmological constraints out from our survey. Okay. Okay, so what we then do is we go from these shapes of galaxies to then the matter distribution. So unfortunately, this graphic may not be that great, but you can get an idea of what we are doing. So we measure the shapes of these galaxies. So the size, there are white lines that you can see on each of these plots. So these are our 4 different redshift bins. And the white lines, the size of the line, it denotes the amount of shear that has been measured on galaxies. So we average on big patches so that we have enough number of galaxies that we can average out the galaxy shape noise. So what you're seeing is a direction and an amplitude for the shear measurement, right? So we can take this shear measurement, then turn it into a dark matter map halfway between the galaxies for which we measured the shear and where we are right now. Okay, so the dark matter map is shown in blue. Okay, so we can make a dark matter map at these 4 different epochs, roughly 6 billion years ago, 5 billion years ago, 4 billion years, and 3 billion years ago. And then we can compare these dark matter distributions to what we get from simulations, and that's how we learn about the cosmological model. That's how we can put constraints on the cosmological parameters. Just to show you, this is the 3D dark matter map of one of the regions that we have observed. This is nearer to us and this is further away from us, and you can see these different structures here. Okay? So we have also done cross-correlation analysis where we take these dark matter maps, cross-correlate them against galaxies to see that where we see a lot of galaxies, we do see dark matter peaks as well. So ours is also the wide but yet sharp 3D dark matter map. The sharpness comes from the fact that we have so many galaxies that we can actually average over smaller regions. So that gives us a sharper map than has been possible before. Okay? So what we are trying to do is this tomographic reconstruction of matter. But then, of course, our main observable is not this. We go to the cosmic shear power spectrum in these 4 different redshift bins, and that's what we try to model to get our cosmological parameters. Okay? So here are the measurements. So you can take the shear field. It's a spin-2 field. So you can decompose the shear field into E and B modes. And these, the E modes, you can take a power spectrum. So that's what's been shown by the red points here. Okay? And then the B mode power spectrum and the cross power spectrum between the E and B modes, they lie here. Okay, so you see, as you have learned in the school, the B mode power spectrums are basically probes of systematics in your data, and so you see that we get roughly consistent values which are consistent with 0 for the B mode power spectrum and the cross power spectrum between the E modes and the B modes. Okay? What you're seeing here is are the different tomographic redshift bins. So this is the lowest redshift bin, then this is further away, this is further away, and this is the highest redshift bin, and these are the cross power spectrum. Okay? So the cross power spectra between the different redshift bins, they come from the fact that there are galaxies which may be common to these redshift bins, so they are probing the same structure. And the other part is from the fact that the higher redshift bin is also going through the same structure as a slightly lower redshift bin, right? So there are also these cross power spectra that need to be modeled, and that's what we put in our model. Okay, so then what you're seeing here is are some gray areas that I've marked out. So we left out these scales from our analysis. On the small scales, it is because of reasons of baryonic effects and our uncertainties about baryonic effects not being accurately taken into account in the model. So we don't want to push to too small scales. And on large scales, there may be some hints of B modes appearing due to systematics in our survey. So we basically clip out these particular regions. So once we clip out these regions, the total signal to noise ratio of our measurement is about 16. This particular CL power spectrum, it can be written as an integration over the line of sight of the matter power spectrum. weighted by these lensing weights, so the geometrical lensing factors. And so that's where our cosmological information is coming from. There's some from these geometrical factors as well as from the power spectrum amplitude itself, amplitude and the shape itself, right? So we have an elaborate model which includes a number of systematic uncertainties as well as intrinsic alignment models and so on. So what you're seeing here is now in a logarithmic scale. And what you're seeing is basically the best fit model, right? So it basically goes through the data points, so there's not much of a problem here. The chi-square is about 45 for 57 degrees of freedom. Okay? And these degrees of freedom, I must say, they account for prior constraint versus data constraint parameters as well. So it's not just a subtraction of all the parameters that we have in our model. The intrinsic alignment modeling, you can see some of these values here. Okay, so they lie pretty much below our main measurement that we are using. We tried to also test impacts of choices and systematics on the amplitude of density fluctuations that we measure. So we have a big systematic error budget. So this is, for example, our fiducial model. We also account for, just check what happens if you don't have any shape errors. What if we use different photometric redshift estimates? What if we fix the intrinsic alignment models or don't have any intrinsic alignment models, and so on? So what you're seeing is the impact on the amplitude of fluctuation measurements here. Okay? So this is where we lie. Our biggest uncertainty may be from these photometric redshift modeling. So that's about 0.5 to 0.6 of the statistical error. And all of these tests, I must mention, were done in a blind fashion. So we did not know any of the values down here. So these were centered around 0 at the time that we did these tests. Okay? So these are all blind results. So then I will go to cross-survey comparisons. So this is between the different weak lensing surveys that are going on. So HSC is here. So that's our result. And then the dark energy survey experiment, it's here. It's pretty much consistent. Then the KIDS 450-degree analysis is here. The power spectrum estimator analysis from KIDS itself is here. So there are some issues that KIDS themselves have to resolve between them. And then the CFHT lens is here. Okay? So what you see is, compared to Planck, all of us lie somewhat lower in terms of the amplitude of density fluctuations predicted at redshift 0. But we ourselves, like individually, we are consistent with Planck. And the same is the case with DES as well. But once you start adding things up and detailed projects where we are doing these joint analysis are ongoing right now, might show up some kind of interesting tensions here. So this is now in the parameter space of omega matter versus this S8, so the amplitude of density fluctuations. And you see that, so our contours are these red contours here, the 68 and 95% confidence contours. In terms of omega matter, we are a little bit lower, but it's still within statistical fluctuation. So we have done these kind of analysis on mocks, and we find that, well, at least 4 to 5% of the time, we can get lower values of omega matter, which are consistent with Planck as well. Okay? So that's where we stand in terms of the analysis. Oops, what happened here? Okay. So then let me go back to the first plot that I showed you. This was the amplitude of density fluctuations as a function of redshift. You can learn something about the dark energy model if you can measure these amplitude of density fluctuations, right? So alone, ourselves, this is the limit that we get on S8 versus W. So we are consistent with W of -1. So these are the blue contours here. Planck lies somewhere here. So that's the gray band. So again, that's like 2 sigma pulling below W of -1. And when we combine HSC with Planck, that's this particular test, then we get W, which is smaller than -1 at quite some significance. Unfortunately, once you add the BAO and the supernova data, we again snap back to the W of -1. So there are some interesting tensions and hints of tensions that are present here. So we will see if these kind of tensions persist as we move on with the HSC survey. So to summarize, this is just the beginning. These were the first cosmological constraints from the HSC survey. This is only from 1/10 of the data that we are going to collect. So it's 140 square degrees. We are hoping to go down to 1,400. Realistically, it might be more like 1,000 square degrees. The amplitude of fluctuation measurements, S8, we nailed it down to 0.8 plus minus 0.03. It's consistent with the expectation from Planck, but it seems like most of these lensing surveys are giving you smaller values of these amplitude of density fluctuations. So please stay tuned for results from HSC, DS, as well as in the upcoming decade from LSST. Thank you.
Question? A mic for him.
I sure. In your list of possible uncertainties, I noticed there was something like AGN. I assume that was something to take into account the effect of baryons, something I'm very worried about in all those analyses. I wonder if you can comment on that, because it seems that how you did that.
So what we have done here is basically we took the OWLS model, so the OWLS simulation suite, and we took the worst feedback model that you can get, or the feedback model which produces the largest deviation from dark matter, assume that to be the truth, and then analyze the data again. So this is the value of S8 that we get. It's, again, comparable to these photo Z systematic uncertainties we moved there. But what we have done as well is to marginalize over this systematic uncertainty. So we take a model where the amplitude of this deviation from the dark matter only prediction can range from -5 to +5. And then we marginalize over all of that as well. And that particular thing, so this AB varied, this leads to a slightly larger error bar as expected, but this is that particular model there. You don't see much of a difference.
So actually it was a related question. So how much of your statistical power is lost due to our lack of knowledge about the feedback, essentially?
Right. So in our fiducial model, we have not assumed any baryonic feedback effects. What we do is we test what happens when we vary this baryonic feedback amplitude, or the difference in the power spectrum in the baryonic feedback models and the dark matter models. We let that as a free parameter, and we vary it from -5 to 5. We fix the shape, but just change the amplitude, right?
Right. If you don't,
and when we marginalize, this is exactly the constraints that we get.
But if you knew the absolute value of the feedback.
Yeah. So then I think we would basically get back to the fiducial value, right? Because there we are saying dark matter only is the case. But it's true that if we knew exactly what the feedback model was, then we can proceed even further inwards. So that will help in the statistical power.
Right. So you would guess that you improve 5% your constraints? Or
yeah, so it depends upon the L values that you trust, right? So again, it will be depending upon the how much you trust your baryonic feedback model.
Okay.
So maybe I can ask a quick one. So there is this Lyman alpha tomography as well that's been done recently. Would cross-correlating that with your maps help in this feedback question at all?
Yeah, so the Lyman alpha tomography will definitely help. Unfortunately, I guess it's in a smaller area, right? It's only in the Cosmos region as far as I understand. But hopefully PFS will rectify that problem. So prime focus spectrograph is a spectrograph on the Subaru Telescope, which is coming up, and it will also do the same kind of region that HSC has covered. But I guess not all of it will be done for the tomography. So in the future, there are, of course, plans to do these kind of cross correlations as well. So on small scales, you can learn about feedback effects, of course. Yeah. Thank you.
Surhud again.